Hi, Jeanette.
Hi.
Nice to see you. Um, all right, so hopefully you guys have had the day to wake up because my second period that's usually pretty decent. It was a complete mess. They were, um, this is the last packet of notes that we're gonna have for the semester. That's it. We're winding down. We basically have 2 weeks of finals prep and then finals, and then that's it. And finals week, you don't even come to every class every day. It's an abbreviated schedule those last 3 days. So, um, we're right here at the end already. Basically, the way it'll work is this week. I have definitely today and tomorrow to um, go over the notes to introduce them. Depending on how fast we can get through it, I don't know if we're gonna finish tomorrow, but I have a Kahoot planned. So that Kahoot is either gonna be on Wednesday or on Thursday, depending on how fast we can get through this. And then anytime we have left over will be to work on the weekly assignment, which will also give you more practice. Next week will be mostly to test on this. We'll have a practice test and we'll have a real test on this last unit, which is on probability. And then towards the end of that week and the beginning of the week after, it'll be to review for the final before we take the actual final. Because we're reviewing for the final, that's going to give us an opportunity for test replacement. I've done everything I can for you guys to pass, and I told this to second period. I'll tell you guys the same thing. I have a feeling that some kids may be under the impression that because last March when this COVID thing hit, you know, I think the word got out that let's just say nobody was forced, but let's just say that the teachers were encouraged to make sure that everybody passed. There was not many kids that failed. There was nowhere near as many kids that failed courses in spring of 2020 than did in previous semesters. That's not the case now. So some of these kids who aren't doing much of anything and not showing up to classes, they think, yeah, but I'm gonna end up passing at the end. Well, they're gonna be in for a surprise. So, from as far as my class goes, I've done everything I can with testing and retesting and replace this grade and replace that grade and like I can't contort myself any more different ways. So that's still gonna apply when we get closer to final review. I'll let you know what grades will replace what grades, and even on the actual final exam, I'll use that I'm sure to replace some other stuff. But at the end, if you end up with a failing grade, don't come and complain to me. So, all right. Any questions? Any questions at home? Any questions here? Can you guys see me and you can see my screen too? Actually, you can't see me yet. Now you can see me. Everybody, Esme, you can hear me. Jeanette, you can hear me.
Yeah.
Okay. The results for the performance final were already put in. No teachers give that back as far as I'm concerned and review it, but the grade is there. If you see your grade and you're like, "Well, that makes no sense. I thought I did perfect and I got a low grade," and you want to talk about it individually, then we can do it that way. But I'm not doing like a group-led review of the performance final. So those grades have been up since before we went on break. Okay. All right. So this last week of this unit, like we started off probability with simple probability, just looking at one single event and learning that probability was, the number of desired outcomes divided by the total number of possible outcomes, right? Then we started kind of venturing into compound probability, which compound means more than one event. Okay, with a focus on or probability. That's what we've covered. Where now, what are the chances of one event or another event happening? What are some words that we associated with or compound probability? It's a quick review. You guys spent all of the Thanksgiving break studying and making sure that you were prepared to come back. So, what are some words that we use to associate with or probability, which is what we focused on before the break?
Union.
Very good. All right. As me said, union. Good. What else? What else do we associate with or probability that I try to ingrain in you? Union is one word. What else? Ouch. Addition. Addition. That the way that you would calculate or probability was by adding. Well, today or this week, we move into and compound probability. Okay. With and, now we're looking at the chances that both events have to occur. But where we differentiate, what you need to establish before you can calculate are whether the two events are independent or dependent, which we'll spend a good portion of today talking about. But before we get into and probability, even though we haven't gone over it in depth, we kind of introduced and probability a little bit, and we talked about some things. So what's some word association that we use with and probability? What are some things that we know are associated with and probability? If you want to know if both events have to occur.
Intersection.
Very good. The intersection is good. If you think about like a two-way table, which you'll see today, if you think about a Venn diagram, we're looking for the intersection, the part in the middle, and what else? And who said that? Oh, that was Mikhail. I just didn't recognize that voice. What else did we, exclusive? No, mutually exclusive, and not mutually exclusive, that's more for or probability. Those are the two different types of or. For and, the two different types of main and are independent and dependent. But what else did we associate? If I just went through the same exact exercise with you on or, right? And I waited, nobody said anything, I said addition. So it looks like the thing I was missing was the operation. I haven't heard an operation yet for and, but we've talked about it before. So what operation do you think you're going to see with and? If we're looking at the intersection of two events happening, what do you think operation we're going to have to use to calculate? It's like literally on the board right now.
Addition?
Multiplication.
Oh, yeah,
multiplication. We're looking at multiplication. Okay? So, now, to figure out what to multiply or how to multiply, we have to establish dependency. So, look, this is not a universal thing, but this is very common, okay? Like, all right, for or, if you're dealing with an or problem, like if they're going to use a word problem, like a lot of times or they do with like playing cards. It's a very common thing. Playing cards are very common for or probability. And I say that, and today you're going to see playing cards, so go figure. But for the most part, when you see something dealing with playing cards, they're dealing with or. Okay, a very common one with and probability are marbles. If you see something like, hey, there's marbles in a bag. So I like to use marbles to try to explain the concept of dependency, whether two events are dependent or independent. So let's think of this. Let's say that there's a bag with marbles in them, right? There's 10 marbles. Okay, let's say there's one red, two blue marbles, 3 green marbles, and I don't have another color, so let's just say there's 4 black marbles. What does that add up to? 10. So there's 10 marbles in a bag, right? And I were to ask you, hey, what is let's go back to simple probability. What's the probability of getting a red marble? 1 out of 10, because there's 1 red out of 10 total. But now let's say, okay, well, what's the probability of getting a blue marble? And what you do with that red marble that you picked out is what determines the dependency. So now my question is, what's my probability of getting a red and a blue? You already told me the red. Okay, red and, listen to the word I said. I said and blue. Red and blue. So if I already got the red, if I were to get that red and put it back, what you'll see is it's called with replacement. If you see the words with replacement, if after I picked out that red, if I put it back, okay, now I'm moving on to blue. It's going to be multiplication because it's and, all right? How many blues were there? There would still be 2. But how many would there be total? If I put the them back inside the bag, how many would there be in total? There would still be 10. These are independent. That second time when I went to pull a marble, effect out the red, and I hold on to it. Okay. Now for that second pull with the blue, there's still 2 blues in there, but how many are there in total in the bag? 9. That creates a dependency, and that dependency changes your overall odds. 1 over 10 times 2 over 10 is not the same thing as 1 over 10 times 2 over 9. You're going to get different odds. So what you'll see there is you'll see the phrase with replacement and without replacement. If you do things with replacement, they're independent. So that sound I hear is you guys writing this down. When you hear with replacement, they're talking about independent. When they're talking about without replacement, it's dependent. In the example with the marbles, if they were to tell you, hey, you pull out 2 marbles at a time, you close your eyes and you reach in, but you're pulling for 2 at a time, that counts the same as dependent because that red marble is still staying in your hands. Like you're going to have both marbles in your hand at the same time. It isn't going to be like one was put back in the bag. So that counts as being without replacement. So now you'll probably find independent conditional to be easier because you're just getting the probability of one times the probability of the other. Easy peasy. But dependent probability becomes a little bit trickier. Okay? So notice how you're still multiplying, but you're multiplying the first event, which like on the example I gave you, was a red marble, but times the probability of the second event on the condition that the first event occurred. This little vertical line I gave you, the probability of, like, for the event 2, which was the blue, there was 2, but on the condition that A had already occurred. And if A had occurred and I pulled out a red, that meant that there would only be 9. So you're still multiplying, but you're multiplying by the conditional probability. On the condition that the first event was successful, what's left over? What are the chances that are left over? These are some formulas that, like, I don't want you to get too confused with this. And there's some other ones up later, but these are some that you're going to want to remember. These usually show up on standardized tests. The probability of, in this case, it's event B happening on the condition that event A already happened, is the probability of both divided by the probability of the one that occurred. If you want some association, whichever one comes second, right, is the one that we've already accepted has occurred, that one goes on the bottom. That's what you divide by. Over here, the probability of event A happening on the condition that event B has already happened is the probability of both divided by the probability of the one that has already occurred. So here's a little example they give you. Now, this is just using the formulas. If the probability of event B is 0.5 and the probability of A on the B is 0.4, find the probability of both. Find the intersection. So, all right, but by the way, these formulas are the exact same thing. These are not 2 different formulas. It's just remembering that the one that has already occurred goes on the bottom. So, but here they gave us already the conditional probability, which is 0.4. Okay, the one that we already know has occurred, okay, which is B, because that's the one that came second, is 0.5, and what they want to know is the probability of A and B. So it's just solving an equation. How would I get this value that I want? How would I get that by itself? How would I solve for that? The opposite of dividing by 0.5.
Multiplying?
Multiply by 0.5. This might seem really confusing, and it's going to make it harder by the fact that you guys are coming off a break and you're still half asleep, but if you pay attention, you see it's not too bad. 0.5 times 0.4 is 0.2. So the probability of both of them occurring The intersection is about 20%. I had some technical difficulties today with second period, so if you guys can be interactive and participate and stuff, like I'm only gonna go as far as I did with them. So if you can do this, we might even be able to finish early today. But if I'm just asking questions and waiting, it's gonna take forever. You toss a coin 3 times. What is the probability of tossing heads, then heads again, and then tails? Okay, and I know it doesn't say the word "and" in there, but this is a specific sequence. They want to know what heads first, heads second, and then tails. It has to be in that sequence. Okay, so what we have to first determine, well, are these independent events or are they dependent events? When I flip a coin, when I'm flipping a coin, is what I get on the second flip going to depend at all on what I got on the first? Does the first flip have any effect on the second flip? Like if I flip tails the first time, am I more likely to get tails the second time also? No, man. Random. When you flip, which one you get, it's completely random. So therefore, when we calculate this probability, it's and probability, so we need to know that we're multiplying. But when we look at each individual event, it's just going to be combining the 3 simple probabilities. There's no condition involved there because it's not dependent. So when I flip a coin, what's the probability of getting heads? What's the probability of getting heads? 1/2. Okay, somebody could have said 0.5. That's fine also, but I like to start with fractions. 1/2. Times. For the second flip, what's the probability of getting heads? Also 1/2. Times. For the third flip, what's the probability of getting tails? Also 1/2. Which if you multiply that, what's 1/2 times 1/2 times 1/2? Remember with fractions, when you multiply, you just multiply across the top and across the bottom. Huh? What's 1 times 1 times 1? What's 2 times 2 times 2? Somebody earlier today told me 6, but it's not 6. What's 2 times 2 times 2? It is 8. And now I mean, see your favorite. Remember, fractions can also be expressed as decimals and percents. So as a decimal, this is 0.125. As a percent, ¿cuál es por ciento? Más o menos, ¿ah? No sé, muy difícil. If you're going to round to the nearest percent, it's around 13%. 12.5 is fine, yes, it's 12.5% if you want to be exact. But if you're being asked to round to the nearest percent, it's around 13. Given a standard deck, look, see, I just finished saying, hey, cards usually deal with or, but in this case it's going to be and. Given a standard deck of 52 cards, 3 cards are dealt without replacement. What does that mean? What did I just finish? If you wrote it down, what does it mean without replacement? It's good. It's going to be dependent. Good. That now, unlike the ones with the coins, the next event is going to depend on the first. And watch it. You're going to see why. What are the probability that all the cards you get are kings? So you go bam, bam, bam. Here's 3 cards. What are the chances they're all kings? I'm not dealing a card and then putting it back. So since these are dependent, okay, what's the probability of the first king? There you go. How many kings are there in the deck? There's 4 kings in a deck out of how many in total? 52. Now, yes, in your head you're reducing it 1 out of 13. That would be correct. But overall, understands it's 4 out of 50. What you said, one, it's the same thing. But this way everybody understands it. Times, since I am not replacing the king, how many kings would now be left for the second king to come? No. I dealt 1 card, assuming that happened, because they can't all happen without the first one happening. The first one has to happen. So if I dealt that first card and bam, there's a king. Now for that second king to come out, there'd be 3 kings left out of how many cards? 51, because that's what dependency does. Is it alters the sample space. It alters the one on the bottom. Okay? Now, again, you cannot get 3 kings without getting the first king, getting the second king. So now when it comes time to get the third king, how many kings will be left? There'd be 2 out of how many? 50. Now, you can try multiplying these like you did on the first one, but that can get kind of tricky. So I would advise you to try to reduce, and actually all of these can be reduced. As Jorge said, this becomes 1 out of 13. This actually becomes 1 out of 17, and this becomes 1 out of 25. Now, you can't reduce any more than that. So that becomes 13 times 17 times 25 is 55. So it's 1 out of 55, 25. Which is it's approximate to 0.0002. Which really wouldn't make sense to go to the nearest percent, because if you go to the nearest percent, you're going to say it's 0%, and this doesn't have a 0% chance of happening, but it's really close to that. So this is about 0.02%. Very, very small chance. To put it in perspective, you'd have to attempt this, in theory, you would have to attempt it, let's see, is that 50 times? Now, I might be calculating it wrong in my head, but I want to say 5,000 times before it happens once. So you'd have to go 3 cards. Yeah, here, I can calculate it. 1 divided by 0.2. 0.2%. So 100 divided by 0.02. Yeah, 5,000 times. So you'd have to go 3 cards, see what you got, put it back. Shuffle 3 cards, see what you got. Shuffle 3 cards, see what you got. And out of 5,000 times, if you repeat that 5,000 times, one of those times you should get 3 kings. Hash brown facts. Any questions there? You guys look as excited as my second period did. In a standard deck of cards, what is the probability of drawing an ace given that the first card was already an ace? And notice how it says no replacement. So when you see no replacement, what does that mean? That means dependent. It means that it's going to be dependent. No, but this is only asking for, they want to know what's the probability of drawing an ace, assuming that the first card was already an ace. So we're not looking at multiple events, we're just looking at one. But if I take an ace out of the deck, how many aces are left? There are 3. How many total cards are left? 51. It's getting awfully quiet at home. So this would give you 1 out of 17. If I divide 1 by 17, that is 0.0588, which is to the nearest percent about 6%. So if now this is not you do not have a 6% chance of going ace back to back. But if we already assume, if you've already assumed that you've taken one ace out of the deck, and you want to know what's the chance of getting another ace, it'd be 6%. Just that second ace is 6%. Does that make sense? All right, let's keep the party going. The probability of spinning a 4 and then spinning again. Okay, we have to establish, are these dependent or dependent? And I realize this gives it away right here, but when you spin a spinner, does what you spin on the second spin, on the third spin, on the fourth spin, does that have anything to do with any spin that came before it? No, they're completely independent. It's the same as flipping a coin. If you flick a spinner and if you play Wheel of Fortune, there's no, whatever you get is completely random. It's not. I'm not going to be more likely to get the bankrupt on Wheel of Fortune if I ended up on $500 the time before. Each time it's completely random. So these are going to be the easier formula. There's nothing too hard about this. It's just going to be like we did with the coins. It's just multiplying each of the independent simple probabilities. So here, let's go with the first one. Well, what's the probability of spinning a 4 and then spinning a 4 again? How many 4s are there on that wheel? Yep, there are 3 4s.
3.
Very good. Hey, somebody at home. Out of 8 times. For the second spin, since the first and the second spin have nothing to do with each other, they're completely independent. I still have the same sample space. There's still a total of 8 spaces. How many of those still are 4s? It's not like we took a 4 off the wheel or anything. Yeah, there's still 3 out of 8, so that gives me 9 out of 64 as a fraction. Then once we go to decimal land, we start rounding. So if we're going to go to 4 spaces, I'm getting 0.1406, which is approximately 14%. 14%. Find the probability of spinning a 1 and then spinning a 2. Okay, so again, these are independent events. One event does not affect the other one. So what's the probability of getting a 1? 4 out of 8, good. If you want to put 1/2, you can also. See, when it comes to OR probability, I prefer to not reduce because you need to have a common denominator when you're going to add, because OR involves adding. But here, if you want to reduce, go for it. Spinning a 1 is, somebody said 4 out of 8. It's also half. Half of the spaces have a 4 on it. A 1 on it. Half of the spaces have a 1 on it. How about 2? How many 2s are there? So just 1 out of 8. That gives me 1 out of 16. Which is equal to 0.0625, which is approximately equal to around 6%. What's the probability of spinning red and then green and then red again? They're completely independent. Just get each simple probability. How many red spaces are there? 2. 2 out of 8 is the same as 1 out of 4 times. How many are green? 3 out of 8. And then red again will be 1 out of 4. They have no effect on each other. Nothing there can be reduced, so this is just going to be 3 out of 128. Which is 0.0234, which is approximately equal to around 2%. Find the probability of spinning blue and then blue again. Okay, how many blue spaces are there? 3 out of 8 times 3 out of 8. It's going to be the exact same thing as it was up here of getting a 4 and a 4. Same thing. 9 out of 64, which is approximately 0.1406, which is around 14%. No questions there. All right, on the next slide, that first question is a repeat, so I'm not going to do that one again, but let's do the one that says number 3. Find the probability of rolling a 6 on one number cube and then a 6 on another number cube. So we have to establish, are those dependent or independent? When you're shooting dice, if you shoot a 1 with one die, am I more likely to get a 1 on the other die also? Is there, does the result on one die have anything to do with what comes out on the other one? No. So these are independent events. So the question is, all right, so how many, so it's a 6 on both cubes. A number cube is nice. What's the chances of getting a 6? How many 6s are there? 1 out of how many total spaces? 6 times 1 out of 6 is just 1 out of 36. As a that's 0.0278, which is around 3%. To try to get something out of my second period today, because they literally were half dead, I just asked them, because a lot of times with dice, they talk about sums. So when you're throwing 2 dice, do you guys know what, when you add them, when you add the numbers up, what's the most likely outcome? What are the 2 dice most likely to add up to? Yeah, when I throw 2 dice, what is the most likely sum to come out? Nobody knows that? It's the and I did this table with them. It's gonna come in the slide. With this shows you you know, what are the possibilities, and as you can see, well, 6 of them. There's ways to get 7. One. This is one. So you're gonna be dependent or thing like you're gonna have to be independent or not. This one is incorrect here. Let's say B. If 2 events are independent, okay, there's a few you can combine, but the same as multiplying one by the other. That one we know already. Looking at conditional probability, the conditional probability is the same as whichever one is listed first. Like, so if I'm looking at the probability of event A on the condition of event B, that ends up being just the same as event A, which, like, when I'm reading it, you think event A happened first, but no, it's actually event B that happened first. We assume that event B happened. So if this first one listed is the same as the as that simple probability, then it's independent. I'll show you an example now. Okay, if the simple probability of event B is the same as their condition. Now they do give you an example here. Okay, but this would be an example using this formula. If the probability of rolling a 6 is 0.17, okay, and the probability of spinning a red is 0.4, usually what they do is they don't hear they're just telling you, but normally they would ask you, are these 2 events independent? And you would check it out and say, okay, well, hey, 0.17 times 0.4, that gives me 0.068. They would also tell you what the combined is, which they do tell you here, that the probability of doing both is that. Do these 2 numbers match up? What they told you and what you calculated, yes, they do, so therefore it's independent. Mitzi, pobrecita. ¿No te sientes bien? No. All right, this will be the last slide. So the quicker we get to this, the quicker we finish. This is the last slide for the day. Even though we had a focus on OR probability, you kind of have been introduced to AND probability because we've done 2-way tables. And 2-way tables is an example of condition. Actually, I need this. So here, let's do some of these calculations which we already know how to do. What's the probability of being right-handed? How many total right-handed people are there? What's the simple probability of just being right-handed? 43 out of
43.
Out of 50.
50.
Yeah. Okay. Which, if you want to go as a decimal, that's 0.86, which is around actually it's not around, it's exactly 86%. Okay. What's the probability of being left-handed? Huh? Yeah, which it's because the other people that are left over, it's just the other 7 people. And I asked my second period. I have more people in person in second period, but like before with Halloween, I was giving out like treats and stuff. I was giving out candies, and this would be a candy question. But I would still ask you guys. I don't have as many people in person here, but do you know what that's called? There was a word we used earlier, like for the left, because it's who was left over. There was only 50 people, so 7 out of 50, which I know is going to be just 0.14, because that's what's left over to get to 1. which is 14%. You guys remember what that concept is called? No, it's the complement, complementary. If you add up this and this, it gives you 1. It's whatever's left over to get to 1 whole. All right, so now the conditional one. The probability of being right-handed on the condition that you... Okay, remember that this little line means on the condition? And what that does is that limits the sample space. So now we're only looking at males. We've already accepted that they're going to be male. How many total males are there? 23. And how many of those are right-handed? 20.
20.
Okay, which now we bring this out. Okay. What's the probability of being left-handed on the condition that they're male? Well, since it's on the same condition of male, it's the same thing as a complement. I know there's still going to be 23 people, but now if I've already used up 20 of them, then I know there's only going to be 3 left. The percentage is going to be 1 minus 0.8696, which is 0.1304, and that is around 13%. What is the probability of being right-handed on the condition that they were female? Okay, how many total females are there? 27. Out of those 27, how many are female? 23. Which now I'll do the calculation. 23 divided by 27 gives me about 0.8519, and that's approximately about 85%. About 85%. And then, and this should say left here. This is a typo. That should say left. The probability of being left-handed on the condition of being a female, that's just a complement. There's 4 people left over, so that's 4 out of 27. I could figure out the decimal by just doing 1 minus 0.8519 gives me 0.1481. All right. So then, part of the reason the problem I had in second period is I was trying to figure out what the heck this question was asking here, and I'm not too sure that I even understand it now what it asked. So I'm gonna just ignore this question, but I'm gonna ask my own question. Okay, which my own question is, all right, here's what's, and it goes hand in hand with this formula here. Okay, they're gonna ask you, are these dependent? So, for instance, if I were to ask you, hey, is being right-handed independent or dependent with being male? Well, if that were the case, then this conditional probability would have to be the same as whichever one you second event. So, like, and up here, I found that probability. That probability was 0.86%. Okay? But it was exactly 86%. But the combined, it's really, really close. I mean, and I could even make the argument that maybe they would be independent because it's just so close. But is this decimal the same as that decimal? No, because one is 0.86 and one is 0.86. And again, they're really, really close, but they're not the same. And you can see it as a percent. No, it's 0.8696. Yeah, so they're really close, but no, you would say that there's a slight dependency there, that they're not completely independent. Okay, look at the female one. The female comes out to 0.8519. Is that the same as 0.86? Because whatever comes first, in order to be independent, all right, this would have to be the same as just the simple probability of whichever one you write first, which is really the second event. Are those two the same? No, they're not. They're really, really close. I mean, this is 85%, this is 86%. It's really, really, really close, but they're not there. You would have to say that they're dependent. There's a slight dependency there. Okay, how about being left-handed? Same thing. Okay, the probability of just being left-handed is 14%. Okay, but the probability of being left-handed on the condition that you're male is 13%. So there looks like there's some slight dependency. And even though over here this rounded, and did I put 14%? Yeah, I did put 14%. They should have rounded to 15%. See what I mean? See, even I made a mistake rounding. They're really, really, really close, but they're not the same. In order to be independent, this would have to be the exact same as whichever one was listed first. And then I think that's why this slide goes on to tell you fun facts that males are a little bit more likely to be males are slightly more likely than females to be left-handed. So there appears to be some type of slight dependency there. That you're more likely to be left-handed if you're a male than a female. If that makes any sense. Any questions for me from home? Did anybody not take the performance final? Because that's the other thing that I have to now try to do is track down and hound the people that didn't take the performance final. You didn't take it? Okay, you need to take it as soon as possible. I'll leave it up. It was the Thursday before we left. So, and that's just one of those things that I have to get you to take it. I mean, I guess it could stay a 0, but people are going to ask me questions as to why it's a 0 if you guys don't take it. So you need to go and do that. Okay. No other questions for me from home, anybody? All right. We'll continue this tomorrow. You guys can go. Well, hold on. Let me see who showed up. I know Mohammed. I think I could see that Mohammed showed up. Did anybody else show up? Mohammed was the one that showed up late, and that's it. All right.